Hello, thanks for watching thanks for committing. Have you committed yet to watching this video? Well, since you pulled it up, I hope so. I don't know if you need more practice balancing aqueous phase redox reactions, but here we go. Here are the rules that I kind of go by and the steps I follow in trying to get these things to balance out. Um, you may or may not be given an equation in the beginning. You really don't necessarily need it if you think about, or if you're told what species are oxidizing and reducing. Think about the two half reactions, definitely, though. Somebody should be gaining and somebody should be losing electrons. Electrons on the right, electrons on the left. You balance the atoms on both half reactions. Usually I just do one half reaction first, then the other half reaction, and then go back and add them together to make sure the electrons all balance out. But I balance the atoms other than oxygen and hydrogen. Then I balance the oxygens by adding water to the side that needs more additional oxygens. I add hydrogens probably to the other side. As I added waters to one side, it creates too many hydrogens, or add hydrogens to whichever side you need it in the form of hydrogen ion. But of course, not all of these are done in aqueous solutions. Some are done in basic solution. Some are even done in neutral solution, which makes it really more difficult. The last step, number 8, is if they're in basic solution, we add OH minuses at the end. When I add the two half reactions back together, I make sure the electrons balance by multiplying perhaps one equation or both by a constant term straight across. But interestingly, let me not say that right now. Rewind that last half sentence. Add the two half reactions together to make sure the electrons cancel. That makes no sense until you try a few. Here's a table I just yoinked off the internet. It's alright. It is a short list. The lists get even more extensive than this. It's a short list of metals and a few non-metals that like to get oxidized and reduced. Lithium, potassium, calcium, sodium love to get oxidized. These will give up their electrons very easily. So if I were to put, say, a piece of magnesium metal into some zinc ion water, what would happen is the magnesium gives up its electrons to the zinc ion in the water, creating purified zinc and causing that metallic magnesium to go floating away in the water as an ion. Interestingly, on this list of metals, we see hydrogen, capital letters asterisk. Doesn't say here, but the reason why is because all the metals up here that are more active or more reactive than hydrogen will be eaten away by an acid, or a simple strong acid, say hydrochloric. But mercury, copper, silver, platinum, gold are below hydrogen, and they are not easily oxidized by that. Oxidized by the hydrogen ion of a strong acid. Similarly, over here, if I bubble, say, fluorine gas through chloride water, the chloride will give up its electrons to the fluorine. So fluorine's more active than chlorine, more active than bromine, more active than iodine. But even still, iodine's used to kill germs. So it's a good oxidizing agent. Let's see. Let's go with the first example. Take magnesium. Oh, no way. I didn't look ahead. I just guessed. I wrote this up a while ago and I'd forgotten that I used magnesium and zinc. So put a piece of magnesium into some zinc ion water, zinc nitrate, zinc chloride, whatever, what have you. The magnesium gives up its electron, 2 of them per, because magnesium is in the 2+ family, and zinc also is a 2+ ion. It gains those 2 electrons. I can kind of see how those electrons cancel. Those 2 equations fit back together to give that one. Or, say, take a piece of aluminum and put it into some nickel ion water. Nickel nitrate, nickel sulfate, nickel chloride, something nickel that dissolves in the water. Well, what happens is the aluminum is more active than the nickel. It gives up its electrons to the nickel and purifies the nickel into pure metal. And I know that based on their positions, aluminum is more active than nickel in the chart. But don't memorize that chart. It's good to think about, though, how some metal might be more active than another one. And I know what some of the more active metals are. You could think about that if you had spare time, but I know you don't, so don't worry about it too much. Take a piece of chromium, put it into some gold water. Man, gold nitrate would be expensive. Why would you spend money on gold nitrate? Anyway, get the gold ion in the water. It's looking for some electrons to take, and it can certainly take them from chromium. And chromium gives up 3 electrons. Chromium gives up 3 electrons to become chromium 3+, and the gold ion takes on 1 electron. But of course, to make this reduction match with this oxidation, I should take this entire equation here times 3. I did it right there. No surprise, 3 electrons, but then in the end I have 3 golds, and 3 golds gaining 3 electrons from each chromium. But non-examples, tin is less active than zinc, so tin will not give up its electrons to the zinc, no reaction. Copper is less reactive than iron, so copper will not give up its electrons to the iron. We also say that the copper cannot displace iron from a compound in an aqueous solution in, say, a single displacement reaction. Another way to say the same thing. Let's look at some nonmetals. And I have fluorine gas bubbled through some iodide water. Fluorine is much more reactive than iodine, so fluorine steals the electrons from the iodide ion, creating iodine, probably solid little crystals, wet crystals. But if I put bromine liquid through chloride salt water, nothing would happen because the bromine is not active enough to steal the electron from the chlorine. Alright, here's another an unbalanced redox reaction. Sulfite goes to thiosulfate. And the nitrite goes to nitrate. We could take the time to figure out oxidation states, but we really don't need to, as long as we separate something into losing or gaining, and the other one hopefully is the opposite. Let's try it. Let's take those 2 half reactions. Here's the sulfite goes to thiosulfate. 2 sulfurs on this side. Let me get 2 sulfurs on this side. That gives me 6 oxygens on this side. This side only has 3 oxygens, so I added 3 more oxygens in the form of water. That gave me 3 times 2 is 6 hydrogens, so I put 6 hydrogens over here. And each step looks even more complicated. The last step is to balance the positives and the negatives. This side had 2 negatives. This side had 2 times 2 is 4 negatives and 6 positives for a total of 0? No. 2 positive. There you go. 2 times 2 is 4 negative, and 6 positive is 2 positive. And this side, therefore, is TOO positive. And so I need to add some more negatives to this side to make the balance with the 2 negatives on this side. I think I decided 4 negatives. 4 negatives, 2 times 2 is 4. 8 negatives and 6 positives make 2 negative overall. Interesting. Messy. Well, if this one's gaining 4 electrons, I hope this one ends up losing some electrons. 1 nitrogen, 3 oxygens, 2 oxygens, so I better add 1 more oxygen to the left-hand side. That creates 2 hydrogens left. Let me get 2 hydrogens right. And that creates 2 plus and 1 minus. This side only has 1 minus, so let me add 2 minus to this side to get this side to the minus and minus balance. Interesting. So now let me take this half reaction, which is now balanced, add it to this half reaction that's now balanced. But of course, before I can add 4 gained to 2 lost, I need to multiply this second equation straight through by 2. So I did it. Because I want this 4 electrons to cancel with that 4 electrons. 2 and 2, so I added those in yellow there. Left everything else alone. Notice what cancels, interestingly, 4 electrons, 4 electrons. 4 of these hydrogen ions cancel 4 of these hydrogen ions, leaving 2 behind. These 2 waters cancel 2 of these waters, leaving 1 behind. And there's my overall balanced redox reaction. Pretty crazy. No way, I don't think you could come up with that without a process something like this. Alright, another one. Interesting. Iodate goes to iodide. Chromium 2 plus goes to chromium 3 plus, separated into half reactions. Work with the half reactions. 1I, 3 O's, 3 O's, 6 H's, 6 H's, and positive, 6 negative, and 6 positive make neutralize to 0, but there's a negative here to match with a negative there. Interesting. This one's too easy. There's no oxygen, no hydrogen, just the chromium. 2 plus goes to 3 plus, and this is 1, 2 positive, so I added 1 electron to that. So how do I make 1 electron lost match with 6 electrons gained? Take it times 6, take it times 6, take it times 6, straight across. And I did that here so that the electrons would cancel. 6 electrons cancel with 6 electrons. Nothing else cancels, and that's my overall right there. Well, these have all been done acidic. I wonder if I have a basic one coming up here somewhere. Cn minus goes to CnO minus. MnO4 minus goes to MnO2. Interesting. Take the two half reactions. 1C, 1C, 1N, 1N, 1O, 1O, 2 H's, 2 H's. And this side has a single negative, that is the side has a single negative. So I better get rid of this 2 plus, 2 minus, balance out. So that I have a single minus on the right, just like I have a single minus on the left. The permanganate's also not too hard to balance. Let's see. 1Mn, 1Mn, manganese, 4 oxygens, 4 oxygens. I mean 1, 2, 3, 4 oxygens. That gives me 4 hydrogens on the right. 4 hydrogens. This side has no charge at all over here, so I want to make this totally neutral as well. 3 minuses, 1 minus, that's 4 minus to match the 4 plus. Take those two half reactions. 2 electrons lost, 3 electrons gained. Shoot, I better take this whole thing times 2. Take this whole thing times 3 so that I can make the 6 electrons gained and lost match up. And what cancels? Electrons better cancel. 6 electrons, 6 electrons. 6 H pluses, cancel 6 of these H pluses. 3 waters over here, cancel 3 waters over here, leaving 1 water behind. And you just summarize again below what didn't cancel. There we go. But if I did this in a basic solution, I wouldn't have these hydrogen ions floating around. So let me add 2 OHs to this side, but I also have to add 2 OHs to this side of the equation to balance everything out. And yeah. So these 2 OHs add with those 2 H pluses to make 2 waters. These 2 OHs just add to the end over here. But this water cancels with one of those waters, leaving only 1 water behind on the left, nothing on the right. And there's my basic solution that I'm allowed in this question. Oi chihuahua. Ah, that's it. Thanks for watching, guys. Try a few of these. They're tricky. Oh, like I think I've said in lecture, the better chance on the exam would be they give you a whole bunch of equations and you're supposed to check and see if that all balances. So if they said acidified solution for this, this would be the answer. If they said basic solution for this, this would be the answer. But you also got to check 2 H's, 2 H's, 2, oh my goodness, 3 carbons, 3 carbons, 3 N's, 3 N's, 2 manganese, 2 manganese, oxygens, gosh, 3 plus 4 is 7, 8, 9 oxygens, right? 8, 9 oxygens left, and 3 negatives, 5 negatives, 3 negatives, 5 negatives. Yep, looks good to me. Alright, see you in lecture.